Bimolecular elimination reaction is an important class of elimination reaction in which strong base is required for abstracting a beta proton while expelling the leaving group from the starting substrate, give rise to formation of alkenes as a product. For example, here we have shown a typical E2 reaction in which the base such as ethoxide is used for abstracting the beta proton. This is beta proton. This interaction expel the leaving group from the substrate and give rise to formation of an alkene. The whole reaction takes place in a single step mechanism, which we call as a concerted mechanism. We call it concerted because both the abstraction of proton and the expulsion of leaving group from the molecule take place in a single step for give rise to formation of alkene. So this is what we call as a bimolecular elimination reaction or dehydrohalogenation, in which the nature and character of base and substrate both are involved for determining the rate of a chemical reaction. Here we have a kinetics, which means that both the concentration of both base and substrate are required for influencing the rate of a chemical reaction. So that's why we call it a bimolecular elimination reaction. As far as E2 mechanism is concerned, there are many factors which influence the rate of E2 mechanism, such as the nature of substrate. For example, we can have a faster E2 reaction in tertiary alkyl halide as compared to secondary, which represent a faster reaction as compared to a primary alkyl halide. This nature of substrate is opposite as compared to SN2 reaction, where a primary alkyl halide promote faster SN2 reaction. But here the bulk of substrate is important because we want to get a stable alkene, and a stable alkene will be obtained only under such situation where the double bond could have a greater number of substituents. In fact, this greater number of substituents could be provided if the starting substrate is bulky or tertiary, or it could have many substituents. So that's why the rate of E2 bimolecular elimination reaction turn out faster in tertiary alkyl halide as compared to secondary and primary. Here we have shown the stability of alkene. For example, a tetra substituted alkene, this is tetra substituted alkene, is more stable than a tri-substituted, this is tri-substituted, which is more stable than a di-substituted, that should be a trans, and trans isomer is stable than the cis, and in turn both are stable than a mono substituted alkene. This is mono substituted alkene. When we talk of stability of alkene, basically we usually refer to interaction of alkyl group with the sp2 hybridized or unhybridized orbital of the pi bond, and this interaction stabilize the pi electronic cloud or the double bond. If there is a greater number of substituents on the double bond, such as in case of tetra substituted alkene, the stability or the interaction will be greater, and we will get a greater degree of stability. So that's why a tetra substituted alkene are more stable than a tri-substituted alkene. So this is the nature of substrate, which is important in bimolecular elimination reaction. As far as the base is concerned, we could have two different type of bases in elimination reaction. Usually in E2 mechanism, we require strong base because it is needed for abstraction of beta proton. So the bases could be of two types. They can be less bulky or more bulky. Less bulky bases are less sterically hindered, such as ethoxide, which is less sterically hindered, and bulky bases include tertiary butoxide, diisopropylamine, and triethylamine. So all these are bulky bases. For example, here we have shown a reaction which proceeds through E2 mechanism, that is concentrated in character. We can control the degree of product formation by using the choice of base. For example, if we use a bulky base, but before addressing the nature of product, we should note the starting substrate, where we have two different type of beta protons. One is sterically hindered. For example, this is sterically hindered proton, and another is less sterically hindered. If we use a bulky base, then it will abstract the less sterically hindered proton, this one. So as a result, we will get a less substituted alkene or a Hofmann product. But if we use a less bulky base such as ethoxide, it will approach a sterically hindered proton easily because of bulk involved. During the course of a chemical reaction, we will get a more substituted alkene, which is known as Zatsu product. So by using the choice of base, we could control the nature or character of the product. If we use a bulky base, we will get a Hofmann product. If we use a less bulky base, we will get a Zatsu product. Here we have shown another typical E2 mechanism, E2 reaction, in which the starting substrate once again has two different type of beta protons. One is labeled as A and another is labeled as B. So we have used three different bases: ethoxide, tertiary butoxide, and a greater or another bulky base. So if we use a less bulky base such as ethoxide, we will get a greater ratio of a stable Zatsu product, that is 71%. If we increase the bulk of a base, Zatsu product will reduce in proportion, that is 28 in case of tertiary butoxide. If we still use a more bulky base, then we will further reduce the Zatsu product and we will dominate the Hofmann product, which is 92 here in this case. Another important feature of E2 mechanism is that both the proton and the leaving group should be in a same plane. For example, here we have carbon, this is hydrogen, this is bromine. So all the four atoms, that is hydrogen, carbon, carbon and bromine, they should be in same plane, or what we call coplanar. But the two groups, especially the hydrogen and bromine, should be opposite to each other or at 180 degree. So such orientation is known as anti-coplanar. In other words, we can say that when we talk of stereochemistry, here we are talking about stereochemistry of E2 reaction. So both the group should be in the same plane or coplanar, but they should be opposite to each other at 180 degree. So such conformation is known as anti-coplanar conformation. Especially when we talk of E2 elimination reaction, the two groups are not exactly at 180. Even many E2 mechanisms or reactions have been found to proceed at appreciable rates, even if the degree is less than 180. For example, 178 degree or 179. If both the group are at 178 or 189 degree, even E2 reaction take place, and such conformation is known as anti-periplanar. So anti-periplanar is more appropriate as compared to anti-coplanar, because we are not certain about the exact degree of proton and the leaving group in the substrate. So it is more appropriate to use anti-periplanar terminology as compared to anti-coplanar, because the reaction can take place even if the degrees are the angle or dihedral angle, which is known as dihedral angle between the two groups, less than 180. It should even if it is 178 or 180, then again E2 elimination reaction take place swiftly. So so far we have talked about different characters of E2 elimination reaction. We have stated about the nature of starting substrate, base and stereochemistry of elimination reaction. So I hope the video lecture has clarified your concept about what exactly E2 mechanism is and how it operates and how it is influenced by the nature of substrate and base.